NENOMATICA, where mathematics meets YouTube excellence. Welcome to our lesson on algebraic identities related to the sum and difference of squares. In this video, we'll explore 4 powerful identities that are essential in algebra, helping us manipulate expressions and solve equations more efficiently. Let's start with our first identity. This identity shows us that the sum of squares of 2 terms equals the square of their sum minus twice their product. The formula states that a squared plus b squared equals the quantity a plus b squared minus 2ab. To prove this, we need to start with the expansion of a plus b squared. We know from the binomial expansion that a plus b squared equals a squared plus 2ab plus b squared. Now, to isolate the sum of squares, we rearrange this equation by subtracting 2ab from both sides. This gives us our desired result. A squared plus b squared equals a plus b squared minus 2ab. Now, let's take a moment to apply this identity. Can you use this identity to calculate 5 squared plus 7 squared by viewing it as the square of their sum minus twice their product? Using our identity, we get 5 squared plus 7 squared equals the square of 5 plus 7, which is 12 squared minus 2 times 5 times 7. That's 144 minus 70, giving us 74. Indeed, 5 squared is 25, 7 squared is 49, and their sum is 74. Moving on to our second identity. This identity relates the sum of squares to the square of their difference plus twice their product. Specifically, a squared plus b squared equals the square of a minus b plus 2ab. To prove this, we start with the expansion of a minus b squared. We know that a minus b squared equals a squared minus 2ab plus b squared. Rearranging to isolate a squared plus b squared, we add 2ab to both sides. This gives us a squared plus b squared equals a minus b squared plus 2ab. Our third identity provides an elegant way to calculate 4ab. This identity states that the difference between the square of a plus b and the square of a minus b equals 4ab. Let's prove this by expanding both squared terms. First, a plus b squared equals a squared plus 2ab plus b squared, and a minus b squared equals a squared minus 2ab plus b squared. Now, when we subtract the second expansion from the first, the a squared and b squared terms cancel out, leaving us with 2ab minus negative 2ab, which equals 4ab. So we have a plus b squared minus a minus b squared equals 4ab. Let's examine our fourth and final identity. This identity states that the sum of the square of a plus b and the square of a minus b equals twice the sum of a squared and b squared. As before, we'll start by expanding the squared terms. We have a plus b squared equals a squared plus 2ab plus b squared, and a minus b squared equals a squared minus 2ab plus b squared. Adding these expansions together, we get a squared plus 2ab plus b squared plus a squared minus 2ab plus b squared. The 2ab and negative 2ab terms cancel each other out, leaving us with 2a squared plus 2b squared, which we can factor as 2 times the quantity a squared plus b squared. So the sum of plus b squared plus a minus b squared equals 2 times a squared plus b squared. Let's summarize the 4 identities we've covered today. First, the sum of squares a squared plus b squared equals the square of their sum minus twice their product, or a plus b squared minus 2ab. Second, the sum of squares also equals the square of their difference plus twice their product, or a minus b squared plus 2ab. Third, the difference of squares a plus b squared minus a minus b squared equals 4ab. And fourth, the sum of squares a plus b squared plus a minus b squared equals 2 times a squared plus b squared. These identities are powerful tools in algebra that can help simplify expressions, solve equations more efficiently, and even perform mental arithmetic more quickly. Welcome to this mathematics video. Today, we'll be solving a problem involving a system of equations and finding the values of various expressions using these equations. Let's look at our example. We have a system of 2 equations, x plus y equals 7, and x times y equals 10. We also have the condition that x is greater than y. We need to find the values of several expressions based on these equations. First, let's find the value of x squared plus y squared. To do this, we'll use the algebraic identity that says x squared plus y squared equals the square of their sum minus twice their product. Now, let's apply the identity. We know that x plus y equals 7, so the square of this sum is 7 squared, which is 49. And twice x times y is 2 times 10, which is 20. Let's calculate. 7 squared is 49, and 2 times 10 is 20. So x squared plus y squared equals 49 minus 20, which is 29. Next, let's find the value of x minus y. We can use another algebraic identity that states the square of the difference of two numbers equals the sum of their squares minus twice their product. Let's apply this formula to find x minus y. We square both sides, and we get the square of x minus y equals x squared plus y squared minus 2 times x times y. Now we substitute the values we already know. X squared plus y squared equals 29, as we just calculated, and 2 times x times y is 2 times 10, which is 20. Simplifying, we get the square of x minus y equals 29 minus 20, which is 9. Therefore, x minus y equals plus or minus 3. However, since we have the condition that x is greater than y, we know that x minus y must be positive. So x minus y equals 3. Now, let's find the value of the square root of x plus the square root of y. We can use the identity that says the square of the sum of square roots equals the sum of the numbers plus twice the square root of their product. Let's start by squaring both sides. The square of the sum of square root of x and square root of y equals x plus y plus 2 times the square root of x times y. Substituting our known values, we get the square of our expression equals 7 plus 2 times the square root of 10. Now, we need to take the square root of both sides. This gives us square root of x plus square root of y equals plus or minus the square root of 7 plus 2 times the square root of 10. But since both x and y are positive, as their product is 10 and their sum is 7, both square roots are positive, so our expression must be positive. Therefore, the square root of x plus the square root of y equals the square root of 7 plus 2 times the square root of 10. Finally, let's find the value of x to the power of 4 plus y to the power of 4. For this, we can use the identity that says x to the fourth plus y to the fourth equals the square of x squared plus y squared minus 2 times x squared times y squared. Let's apply this formula. We already know that x squared plus y squared equals 29, so the square of this expression is 29 squared. And the square of x times y is 10 squared, which is 100. Let's calculate the final answer. 29 squared is 841, and 2 times 100 is 200. So x to the fourth plus y to the fourth equals 841 minus 200, which is 641. Let's begin with our example. If a plus 1 over equals a, find the value of a squared plus 1 over a squared, where is greater than 0. First, let's identify what we know. We're given that a plus 1 over equals a. Let's call this equation 1. To find a squared plus 1 over a squared, we'll use a mathematical identity. When we square the binomial a plus 1 over a, we get a squared plus 2 times a times 1 over a plus 1 over a squared. This simplifies to a squared plus 2 plus 1 over a squared. Now, we know that a plus 1 over a equals a from equation 1. So, the left side of our squared equation is a squared. This means a squared equals a squared plus 2 plus 1 over a squared. Finally, let's solve for a squared plus 1 over a squared. We can rearrange our equation to get a squared plus 1 over a squared equals a squared minus 2. Therefore, we've found that a squared plus 1 over a squared equals a squared minus 2. This is our final answer. A squared plus 1 over a squared equals a squared minus 2. Let's verify our answer with a simple example. Suppose it equals 2. Then 1 over it equals 1/2. So, a plus 1 over it equals 2 plus 1/2, which is 2.5. This means a equals 2.5. Now, let's calculate a squared plus 1 over a squared directly. A squared equals 4, and 1 over a squared equals 1/4. So a squared plus 1 over a squared equals 4 plus 1/4, which is 4.25. Let's also verify using our formula. A squared minus 2. A squared equals 2.5 squared, which is 6.25. And 6.25 minus 2 equals 4.25. Great! Both methods give us the same answer, 4.25. Which confirms our formula a squared plus 1 over a squared equals a squared minus 2 is correct. Let's visualize this relationship in a geometric way. Imagine a square with side length a giving area a squared, and a small square with side length 1 over a, giving area 1 over a squared. Welcome to this mathematics lesson, where we'll solve an algebraic problem involving radicals and substitution. In this problem, we're told that a plus 1 over a equals a, where a is positive. We need to find the value of the square root of a plus 1 over the square root of a. Let's start by defining what we're looking for. We'll set south equal to the square root of a plus 1 over the square root of a. This is the expression we need to evaluate. Now, let's try to relate this to the given information. One strategy is to square our expression s. When we square s, we get the square of the square root of a plus 1 over the square root of a. Using the binomial formula for squaring a sum, we get a plus 2 times the square root of a times 1 over the square root of a, plus the square of 1 over the square root of a. This simplifies to a plus 2 plus 1 over a. Looking at our simplified expression, we notice something interesting. The terms a plus 1 over appear in our expression. We know that a plus 1 over equals a, so we can substitute this into our equation. This gives us s squared equals a plus 2. Now that we have s squared equals a plus 2, we need to solve for s. We take the square root of both sides. Since we know that it is positive, s is also positive, so we only consider the positive square root. Therefore, south equals the square root of a plus 2. Therefore, the value of the square root of a plus 1 over the square root of a equals the square root of a plus 2. Let's verify this is correct by going through a quick example. Let's summarize what we've learned. In today's video, we'll solve a geometry problem involving a rectangle and the Pythagorean theorem. Let's get started. Let's start with our example. If the diagonal of a rectangle is 17 units, and the difference between its two sides is 7 units, find the area of the rectangle. Let's visualize this problem by drawing a rectangle. We'll call the length and the width b. The diagonal forms a right triangle with the sides of the rectangle. We're told that the difference between the sides is 7 units, so we can write a minus b equals 7. And the diagonal is 17 units long. Now, let's set up our equations. First, using the Pythagorean theorem, we know that the square of the diagonal equals the sum of the squares of the sides. So, d squared equals a squared plus b squared. Since the diagonal is 17, we have 17 squared equals a squared plus b squared, which gives us 289 equals a squared plus b squared. We also know that a minus b equals 7. Let's recall a useful algebraic identity. A squared plus b squared equals the square of a minus b plus 2 times a times b. Let's use this to help us solve the problem. Now, let's substitute what we know into this identity. We know that a squared plus b squared equals 289, and a minus b equals 7. So the square of a minus b is 49. Substituting these values, we get 289 equals 49 plus 2ab. Subtracting 49 from both sides, 240 equals 2ab. Dividing by 2, 120 equals ab. Since the area of a rectangle is length times width, or a times b, we've found that the area of the rectangle is 120 square units. Let's visualize our rectangle in 3 dimensions to better understand the problem. Welcome to our math lesson. Today, we'll solve a problem about perfect square trinomials. Let's see how to find the value of parameter that makes an expression a perfect square. Let's start with our example. We have the expression x squared plus 2 minus 6 times x plus 36. We need to find the value of parameter that makes this expression a perfect square trinomial. To solve this, we need to recall the form of a perfect square trinomial. A perfect square trinomial has the form of bracket a plus b close bracket squared, which expands to a squared plus 2ab plus b squared. Let's assume our expression x squared plus 2 minus 6 times x plus 36 equals bracket x plus some number p close bracket squared. If we expand the right side, we get x squared plus 2px plus p squared. Now we can compare the coefficients on both sides of the equation. For this to be a perfect square trinomial, the coefficient of x must be 2p, and the constant term must be p squared. So we get 2 minus 6 equals 2p, and 36 equals p squared. From the second equation, we can find the value of p. P squared equals 36, so p equals plus or minus 6. Since we're working with a perfect square trinomial of the form bracket x plus p close bracket squared, p should be positive. so p equals 6. Now that we know p equals 6, we can substitute this back into our first equation to find the value of a. We have 2a minus 6 equals 2 times 6, which gives us 2a minus 6 equals 12. Adding 6 to both sides, we get 2a equals 18. So a equals 9. Let's verify our answer by substituting a equals 9 back into our original expression. We get x squared plus 2 times 9 minus 6 times x plus 36, which simplifies to x squared plus 12x plus 36. This matches the expanded form of bracket x plus 6 close bracket squared, which is x squared plus 12x plus 36. So our answer at equals 9 is correct. Let's visualize this geometrically. A perfect square trinomial can be represented as a square with side length x plus 6. The area of the square is x plus 6 squared, which equals x squared plus 12x plus 36. The coefficient 12x represents the sum of the areas of these two rectangles, each with area 6x. Quick challenge for you. Can you find the value of a that makes the expression x squared plus 2 a plus 4 times x plus 25 a perfect square trinomial? Pause the video and try to solve it yourself before we continue. Let's summarize what we've learned. A perfect square trinomial has the form bracket x plus p close bracket squared, which expands to x squared plus 2px plus p squared. To find the value of a parameter that makes an expression a perfect square, we compare the coefficients with the standard form and solve for the unknown. In our example, we found that a equals 9 makes the expression x squared plus 2 a minus 6 times x plus 36 a perfect square trinomial, specifically bracket x plus 6 close bracket squared. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.